Okay, thank you very much. And thanks for organizing this event. It's been amazing so far. So when I first sent this abstract, it was a while ago, I was a bit obsessed with de-hyping quantum computing. And one of the obsessions was to better understand what is the power of quantum computers, no? So how do we compare it? What are the metrics that make it so nice? And energy consumption is, of course, one of it. And I had this side project that I'm going to explain. But as things move very fast in startups, my role changed also very fast. And now I was removed from this project because I couldn't. I'm now the current CEO of the company, so I don't have time to do that much technical work. And I let my colleagues, Jose Miralles, Jordi, and Joffre to do the real job. So today I'm presenting their work. So if you have certain questions that I don't know how to answer, please apologize. I will ask them, and I will let you know straight away after. But okay, so now I'm representing this team. This team is Kilimanjaro Quantum Tech. We are a full-stack quantum computing company based in Barcelona, in Spain. And we are a bunch of physicists, engineers, systems architects, strategists, and business people that we are building quantum as a service based on analog systems. And what is our philosophy? What is our approach? What is our vision? So we think that all quantum computing companies, if they really want to survive, should really focus on showing some quantum advantage, some quantum practicality outside of the labs that can be of any use for some industry or some specific applications. And it's challenging, and we all know that. It's really difficult, and we are still far away, and there's a lot of progress to happen yet at the engineering and at the research level. But our approach is to, in order to bring this forward, to maybe start small. In Spain, we say, don't start the house from the roof, start from the base, and let's build on complexity. So what we focus is on quantum app-specific devices based on superconducting qubits that we tailor very much to a specific use case. And we try to, in this approach, in this way, see if we can maximize the technological capabilities of quantum computing and see if we can find an application, if we are lucky, where we can really show a quantum advantage. And this is our differentiated architecture. We focus on flux qubit device, and we focus on the analog quantum computing paradigm, no digital computation. We focus a lot on coherent flux qubits for our simulators and annealers. And we also focus very much on having interactions between the qubits that go beyond the ZZ interaction, so we can go beyond the Ising model. We focus also on following a co-design approach. We are three main technical teams focusing on applications and theory, hardware and software, and we work in a very integrated manner in what we call a co-design approach to try to maximize the different teams' knowledge and languages. And this is our roadmap. I'm going to go very fast through this. We started building our labs and our infrastructure in order to create all the layers necessary to offer this quantum as a service to the outside. We want to offer this remote access so users and researchers can try it out. And we want to have it very open, including the software, the algorithms portfolio, and so on, and all the backends. And in these backends, we start including digital QPUs this year, that I'm going to show you now and talk a bit about that. And next year, we're opening it to the public with all the analog solutions that we have been developing during this time. And one achievement that we've done in this roadmap is to deliver the first quantum computer in Spain. This is a tender that we won on putting quantum computers in an HPC center. This is the BSC, the Barcelona Supercomputing Center, and this is Mare Nostrum. This is considered the most beautiful supercomputer in the world, and I admit that it really is. It's in a small church, and it's really nice to visit. And the quantum computers that we've assembled and integrated together now are in our lab, and we are providing service remotely, but they will go in the first row of the church. So it will be a very nice picture to see very soon. And, okay, this is a video. While what we've been doing in this project is not really developing our analog formula or analog architecture, but working with digital systems. So we've been serving as integrators, if you like, and putting everything together, getting in charge of the supply chain, but the chips are not ours. The chips are digital superconducting-based qubit chips from different providers in Europe, including Quantware and IQM that you heard Jan's talk yesterday. But we have this knowledge, and while we develop our research and innovation, we can also provide this to clients that really like that. But today, okay, how can I stop that? But today, I'm here to talk about this project that I was in a few months ago, and that now my colleagues are taking care of. This is a project called QUCO. QUCO is a public project that is financed by the CEDETI and the Spanish Ministry of Science, and that it contains a big consortium of companies and research centers there in Spain. And the intention of this project is to evaluate the impact of quantum computing for strategic industries. And that's why this is a consortium with industries such as Repsol, which is a big energy company, BBVA, which is a big bank, and so on and so on. And what do we want to do in this project? What is Kilimanjaro side here? So Kilimanjaro side was to try to understand from the benchmarking and metrics how we can compare quantum computers and also quantum computers with classical computers. Because we always talk about the power of computation, quantum computation with this new qubit encoding, exploiting the quantum effects, such as superposition, entanglement, tunneling, blah, 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 and that this can provide faster solutions, better accuracies, and more sustainable ways of doing computation. This is what we say. We love saying that. But is this true or this is hype? And the other way to show it and really argument it with numbers and with a scientific rigor is to prove it. And I think QEI is doing a good job here on trying to ask the question of whether quantum computing is actually a more sustainable way of doing computation. And what is the way we have to prove this type of claims? Nothing more than benchmarks. And benchmarking is a really important process that will take a lot of time, that it takes a lot of discussions. It's not an easy thing to establish what are the right benchmarks, but we really need to make an effort if we want to keep making these claims. So what we've been done, we have tried to work on defining what would be the ideal benchmark, not only for energy consumption, but also for time, accuracy, et cetera, et cetera. And we came up with 4 main properties that a benchmark should have. Should be randomized, so formulated on a random basis, covering a wide range of scenarios, so not judged on a very specific task. Should be holistic, so it should be a high level without focusing on any individual metric, but maybe unifying more than once. So it's not only about energy consumption, it's about speed, it's about accuracy, we're talking about coherences, fidelity, so on, so on, so on. So how we unify all these metrics? It should be platform independent. There's a wide variety of architectures for quantum computing, and we should have a way to compare between them. And it should be very clearly defined. So the protocol used to execute these benchmarks needs to be very easy to follow. And we've been working on 2 types of benchmarks. We have separated them because we saw some confusions. We divide them in system-level benchmarks, where we evaluate coherence, topology, fidelities, et cetera, et cetera, et cetera. And then on application-level benchmarks, where we have a suite of some applications. The ones that we've been studying are mainly quantum chemistry and binary optimization applications that you run and you get some score. This is typical. This is similar to how you benchmark classical computers or supercomputers with LIMPAC and so on. So today I want to talk about also these application level benchmarks with a bit more detail, because you have relevant measures that you can include. You can explore. The 2 first ones concern the accuracy of the result, optimality gap, normalized fidelity, etc., etc. The 2 second are more related to time, gap at time, time to target, runtime, etc. And the last one, the one I really want to focus, is the energetic cost. The problems under study that we are developing for these benchmarks are simulations of molecules, very simple, and optimization problems as well. And for the visualization, what we see in the literature and also what we are developing is these volumetric benchmarks, where you can, on the y and z axis, you have some parameters such as energy and time, and for the z-axis you have the quality of the solution. So you can involve more things. But while we were working on this and trying to think how we would study the energy consumption, we realized that there are no real tools to do that. So we had to go to the engineers of ourselves, actually, because we did it ourselves without being engineers, and we had to develop some tool, basically, to be able to study the consumption of our lab. And we just bought a bunch of sensors, energy meters. These are the ones that are in the picture. And we started installing them in the different components that we have in the lab, the amplifiers, the control electronics, the server, the microwave generators, and so on. And we also made some assumptions. We didn't install those on the fridge or on the compressors or on the chillers. And we made a sum up of what we call a needle state assumption. So we consider these consumptions to be constant during the computation. And this is the systems architecture that we built. It's very easy. You install the sensors in your lab, then you use an MQTT protocol to do the communication through a telegraph plugin that sends all the information live into an influx database, and then you can visualize it from a Grafana. And we made this repository public, so if anybody in a lab wants to install and use this system, you are free to take it and do it yourself and play around. We also included a monitoring tool for that, and we are tracking constantly all the consumption of all this equipment, and we are starting just now to make some conclusions and getting some results. So the first one is we've been evaluating the consumption of the operation of a 5-qubit superconducting chip based on transmons. We used randomized benchmarks of only random single qubit gates for this case. And what we realized is that with the number of qubits and the circuit depth, you don't see a big increase in the energy consumption of your system. What you really see is an increase as you grow the number of shots that you perform, also for measurement. So this is one of the first results that we got with all this setup. Makes sense. We want to now go much more in detail. And the next thing that we wanted to evaluate is how these randomized benchmarks compare between single qubit gates only and 2 qubit gates only. And we see that 2 qubit gates indeed take more consumption than randomized single qubit gate circuits, which also makes sense. And what we are noticing is that this comes from a potential saturation of the cooling mechanism for the control electronics, which basically this is the fun having to work higher. But we are still investigating this in detail. Now, the thing that we really want to do is take all this setup now that we have installed and find the right benchmark to compare it with HPC. So we are doing this project also in collaboration with the Barcelona Supercomputing Center. Jofre and Artur are working from there to also study with a lot of detail what is the energy consumption of a typical HPC process. And for that, we are using the EAR, which is a tool that has been actually created at BSc by a spin-off that is called Energy Aware Solutions, that really focuses on developing software to understand better the detail of the energy consumption of a computing algorithm or a computing process. So we are using this and also Slurm, that many of you might already know, to understand better the complexities of the consumption in a large supercomputer. Yes, because as you can imagine, it's not trivial, it's not as easy as installing the sensors in a lab. You really need to go node by node, you really need to look into the different type of memories and so on and so on and so on. And we are now preparing this for the, now these calculations are for the Mare Nostrum 4, but we are preparing also to be able to calculate the consumption for Mare Nostrum 5, which is going to be one of the 8 biggest HPCs in the world. And what are the next steps? So we really want to now exhaustively study the consumption of different operations in the quantum system with the scaling considerations. So we want to see how the system changes, how the consumption changes with number of qubits and different operationals, different algorithms. And we really want to find a way to really have a one-to-one comparison between a simulation in HPC and a simulation in quantum computers. One option, and the thing that we're going to do next, is to literally simulate the same randomized benchmark that we've done in the quantum computer and see how it scales. We also want to evaluate different architectures, so not only the transmons, we also want to see how transmon versus flux qubits change, and also how algorithms from the digital and the analog paradigm of computation make a difference in terms of consumption as well. And having said that, we really want to improve this open source tool that we are generating and documentation to have a standard way to compare among machines. So please feel free to propose any ideas or any benchmarks or something that comes to your mind, and we'll include it and share it with everybody. And with this, again, if you want to look at the tool, you can access the GitHub, and if you have any questions, you can write to any of us. Thank you very much.
Thank you very much, Marta, for this nice talk. Are there questions? So, again, I have one. So I'm actually quite impressed to see how far you go to really do all the monitoring and so on of the energy consumption of your quantum computer. And I'm interested because if I understand correctly, what you end up doing is putting sensors more or less everywhere to track all the energy consumption and so on. So do you have an idea of, is this scalable in a way? Like if you go to, let's say, an IBM machine of 500 qubits, do you have to put more and more and more sensors? And can you track this? Or is there at some point that this just kind of levels off and that you say, with 20 sensors I can get everything?
Well, I think eventually you know how the control electronics scales with a number of qubits, and you shouldn't have to put one sensor per cable because more or less you're going to see the same behavior. So yeah, that wouldn't scale very well. You have to put a sensor for a machine with 400 qubits due to all the related electronics and infrastructure that goes around your fridge. So I think with just a couple would be enough, and you then can do the extrapolation and see your result.
Okay, thank you. Are there, there is a question there in the back.
Right, can you hear me this way? Yeah, okay. Very interesting talk. This looks really very promising, as already the chair said. I wonder, I am not in the technology sector, but I know that, you know, IP is very important. Can you hear me? No? Okay. Why? I can hear me double. How can you not hear me? You can hear me. Maybe I need to sit somewhere else. Maybe the place where... Right. Can you hear me now?
Yeah.
Okay. It may be the place where I was sitting. Yeah, I was saying very, very nice talk, very interesting results, and indeed very far ahead in this business. And I was wondering, so I'm not in industry, I'm wondering though, isn't it so that IP is really important and patents and all that? And can you actually use your advantage that you now have in this field of already putting in an effort into, you know, measuring the energetic cost and so on? Can you actually use that from the industrial point of view to already claim some IP or patents or so, or is this soon on your horizon?
I didn't understand the last question, sorry. Did you say about something? Sorry, I cannot hear very well.
Okay. Okay, I am loud.
So as far as I understood, so the question was about IP, intellectual property, whether doing this for, let's say, open source, whether this is...
Yeah.
whether this is basically losing your commercial
Okay,
advantage
okay,
or
I see
competitive
what you mean. I more or less got that. So yes, we could, if I understood the question, you are asking if it's worth to protect this, and I think it's really not, because it's for the benefit of everybody. So my vision in quantum computing at the moment is that it's a time to really cooperate and work together between research institutions and between companies. Of course, there will be a level of competition eventually, and there's already a level of competition. But I think for benchmarks and for comparisons and to advance and to show the potential of quantum computing, this is the benefit for everybody. So sharing these benchmarks, these ideas, I think it should be a common effort. And actually working on the standardization should be a common effort rather than having every individual company duplicating work and doing the same investigation. So that's why we decided to share this.
Okay, are there any further questions? So I have maybe a second one. I don't know whether you already looked at this, but given that you're in an HPC center, that you have this, or building this interface with a quantum computer and monitoring everything, I'm a bit curious whether on the classical computing level, whether there is an additional energy cost at actually having to do the interface with, or the interaction with the quantum computer.
Actually, that's a very good question, and this is something that we could study, because we will have this opportunity, right? So we are integrating quantum computers with HPC centers and systems, and we can see what is the extra cost. But I would expect that it wouldn't be the interface that you need to put to connect the two machines. I wouldn't expect it to be very high in consumption, to be honest.
Okay. So I look last time inside the audience, I see no hands, so then we thank Marta again for this nice talk.